All right, after contemplating and deciding to film 2 video lessons in one day, I must admit the amount of work put into the first one was quite exhausting. I don't know how much energy I have left, but I'm gonna make sure to power through this, right? To make sure that I can really lift things up and feel very vertical about my thoughts and feelings towards our next idea, which is vertical work. So going back to the idea of horizontal work, right? Work is a force that is applied over some distance, right? That is going to cause an object to change its motion, right? You're going to apply a force, that object has to move, and then work is being done, caused by the force that is acting in the direction of displacement. So now if we lift something up vertically, you gotta think to yourself, well, what is the force that's actually acting here? And that's gonna be the force required to lift the object up. So if you try to pick something up and you can't, it's because you're not exerting enough force to be able to cause that displacement to happen. So whatever the minimum amount of force is to lift the object up, that's what it's going to take to do vertical work. Could you do more, exert more force than that? Absolutely you could. Remember, the more force you apply than necessary, the greater acceleration you're going to cause it to undertake. And the displacement, rather than calling it just an arbitrary amount of displacement, it is specifically the height, right? So the height change that the object is going to undergo. So if you lift an object up 7 meters, that means that the height changed by 7 meters, right? So we would go from that starting point to the ending point. And that becomes pretty important. You have to make sure you know, what are you measuring that height with respect to? Are you measuring it with respect to a lab bench? Are you measuring with respect to the ground, with respect to a table height, with respect to a chair, right? You have to know, what is your initial height considered, what is your final height considered, and ultimately, if that object were to fall, what is it going to fall back down and hit, right? Where is it going to make contact? That's how we can determine the height. So for example, with that height, if I take a ball, right? So if I take a ball, and if I hold the ball above the bench, right, so if I back this up, if I hold it above the bench, it's going to fall and it's going to make contact with the bench. Well, now, if instead of the bench, I hold it over the floor, well, now the height would be measured with respect to the floor, right? So the work it takes to go from the bench to this height would be different than to go from the ground to that same exact height. It depends on where you are measuring from. So our formula that we would look at here is going to be slightly different, but at the end of the day, it's going to hold the same properties and the same characteristics as our general formula for horizontal work did. We're still looking at force times displacement, but now our force is going to be the weight of the object, because in order to lift the object up, you have to apply an equal amount of force to its weight. So it's going to be the weight of the object, F of G, times the height that it has been moved. Now, the height that it's been moved from, and that kind of goes back to the example I was just doing, if I go from here to here, that distance is going to be some amount of work. If I start it at a lower height and move it the same height, right, that is then going to be the same amount of work. As long as the height change is the same, it doesn't matter where it starts or where it ends, that height change is the same, we're still good. If you reference it from a specific location, that's when it becomes important, right? So if we say, hey, we move it 2 feet up from the lab bench, or if I say, hey, let's move it 6 feet up from the floor, I could be at the same height off the floor, but if I'm measuring the height from the lab bench versus from the floor, we're going to get different results. And remember, we can break the weight down into mass times the acceleration due to gravity, so we can have mgh is what we can be looking at here. Now, a quick example, right, just to utilize this here. How much work is needed to lift this car, right, that sweet green clip art car, which has a mass of 1.998 kilograms, 0.45 meters. So we would have the mass, m, we know g is 9.81, and we know what our height change of 0.45 meters is. So if we plug that in, we get mgh, we get 8.8 joules, or 8.8 Newton meters. Now, maybe asking yourself 2 questions, right? First question, hey, what about angles, right? What about angles, right? How does the angle work here? Well, if you're lifting the object vertically and it's moving vertically, that angle is always going to be 0, right? If we're going to lift an object straight up, right, we're going to be looking at an angle of 0 here. Technically, could you apply a force at an angle to get it to move vertically? Absolutely. We're going to look at kind of what that looks like on the next slide. But in general, we're not going to be dealing with angles when talking about vertical work. Again, in general. Second question you may be asking, well, boy, that 0.45 meters, where's it measured from? Technically, it doesn't matter, right? It doesn't matter if that 0.45 meters is from the ground, if it's from some arbitrary height and you moved it up 0.45 meters. The amount of work it's going to take to move that 0.45 meters vertically is going to be the same regardless of what its starting point is and what its ending point is. The height change is 0.45 meters. That's what's important. So then what about ramps? Right? And ramps is where we start to see the application of our angles here to vertical work. But what's their purpose, right? Do they actually allow us to do less work? Do they really make it easier for us? And our perception of ease comes down to the amount of force that we have to generate, not the amount of work that is actually accomplished. So what we see here is we have that same cart, and now we're going to apply different amounts of forces based on the angles that we see in these ramps. So we have a 30 degree, a 45 degree, and a 60 degree ramp. The cart has the same mass. And what we would know, right, if we wanted to get this height to be at 0.45, we would know that the force required to lift it, if there's no ramp, is going to be this 19.6 newtons. But the work to get the car to the top of the ramp is 8.82 Newton meters. So if we watch what happens here, check out these three vehicles are going to go simultaneously, and they're going to move a little bit. So note the displacements on each one of these, 0.1, 0.071, 0.058. The shallower angle has a greater displacement, but the work done is still the same. It requires less force on that lower angle, but it's a greater displacement. The 45 degree in the middle amount of force, middle amount of displacement. The 60 degrees is going to require the most force, but the least amount of displacement. And as this continues, we're going to notice that trend is going to stay the same, where the work done is identical, but the displacements are different because the forces are different. So as it moves to that same height, the displacement on that shallower ramp, it requires a greater distance on that shallow ramp for less force. And that's why we say, oh, I'm going to use a ramp because I'm not going to have to work as hard. Well, again, you're working the exact same. You just have less force to exert, but you have to exert that force over a greater distance. You know, it's like saying, boy, you know, if I've got to move some furniture, it's way easier to walk a furniture up a ramp than it is to straight pick it up because that furniture's heavy. You use the ramp so you don't have to exert as much force. The more you get towards 90 degrees, right, so the more vertical you get, the more force you have to exert, but you don't have to move it as far to reach the same height. And that's the big idea here at the bottom. The work is the same. However, we're going to use ramps to reduce the amount of force that we need to exert, but you then need to exert that force over a much greater distance. So shallow angles use less force over a great distance. Steeper angles are going to use more force over a shorter distance. At the end of the day, the net amount of work done is going to be the same. So here'd be an example of vertical work. We're going to get a bunch of hoses underneath this shell of a car, and it is going to lift the vehicle up. So if you watch, you're going to see when work is done and when work is not being done. As long as this vehicle is in motion, work is being done. So it's moving, work is being done. Work is no longer being done right now because we're not in motion, right? No motion, no work. And then there, work is done again as that car falls back down. Remember, work depends on motion. It took work to get the vehicle from the ground to that maximum height. That took work, right? It had to exert force over whatever height it reached. Once it got to that max height, work was not being done. Then when they turned the water off, work was then done by gravity, by the force due to gravity, to pull that car back down. So work was done when it was in motion, moving upward, and then work was done as it was moving downward. So here's a quick example of vertical work. So we want to know what the mass of a barrel lifted 3.5 meters vertically by Donkey Kong if the work done is 1,550 joules. So find the mass given the height, the vertical change in distance, right? So 3.50 meters, or the vertical displacement, 3.50 meters. The work done is 1,550 joules. Take a moment and solve this problem, and then come back to the video. Okay, welcome back. Here's how we would solve this problem. So we know vertical work, MGH. We're solving for the mass, so we're going to take work divided by the acceleration due to gravity times the height that the barrel is lifted. So mass equals work divided by G times H. We know the work is 1,550 joules, or it could be 1,550 Newton meters as well. That is an acceptable value for work. We're going to divide that by 9.81 meters per second squared times 3.50 meters. Make sure as you're doing that denominator, you solve out the entire denominator first, then divide 1550 by it, or put the entire denominator in parentheses. So the mass of this barrel is going to be 45.1 kilograms that Donkey Kong is able to lift vertically, which makes sense. Donkey Kong is quite the impressive Mario universe character, right? Real big, real strong, likes to throw bananas. It's a good time. So that's what we have here for vertical work. Again, just the work done to lift an object, and we see it's not drastically different than the work done horizontally on an object. We just make a few modifications where we're actually looking at the weight of the object times the height that it moves, as opposed to the force being applied and some distance it moves horizontally, right? So it's about that vertical force, which is going to be our weight, and it's about the height that it moves. And that height, make sure you know what that height is referencing, right? Is it an arbitrary 3.5 meters? Is it a 3.5 meters above something, right? Make sure that you know what those heights are and where they're being measured from if that information is given to you. Thanks, guys.